In this new section, we're going to solve some binomial distribution problems, except we're going to assume that it's normal, and we're going to use normal to approximate the binomial distribution. There are some criteria that have to be met prior to being able to use the normal distribution techniques. N, the number of trials, times P, the probability of success, must be 5 or more. Likewise, N times the probability of failure must be at least 5. If these two criteria have been met, you could solve this binomial problem, or you could approximate the answer to this binomial distribution problem by using the normal distribution techniques. Let's consider this first problem. Suppose that the chances of having a boy or a girl is a half. You're pregnant, you're going to have a child, half the time it'll be a boy, you have a 50-50 chance for it to be a girl. And the question is, suppose that you're going to have 35 girls out of, say, 75 births. Actually, we want to find, see if I can sneak this in, we want to find the probability of more than 35 girls out of 75 births. Okay. Now, the way you would do this as a binomial distribution is this probability of having more than 35 girls out of 75 births. Well, this would be a straightforward problem. More than or equal to. More than or equal to. 35 or more out of 75. And how you would do this is you'd find the probability of having exactly 35 girls out of 75, plus the probability of having exactly 36 girls out of 75, all the way up to the probability of having exactly 75 girls out of 75 births. There are not 3 probabilities that are being added. There are many in here. Probability of getting 37 girls out of 75. Probability of getting 38 girls, 39 girls, plus the probability of 40 girls, all the way up to 75. In fact, there are 41 calculations. There are 41 of these that you would have to find. I guess 38 of them are in here, because 38, 39, 40, 41. How would you find, for example, the probability of 35? Well, from the 75, you want to choose 35. And you have the probability of having a girl, that's collect success. Probability of not having a girl. Well, 35 times we do want a girl. And if you're having 75 kids and 35 are girls, it's reasonable to assume that 40 are boys. And you'd have to work this out. And then you would have to do the probability of getting 36 girls. So from 30, you want to pick 36, from 75. A lot of ways of doing that. You have the probability of getting a girl, and you want 36 of them, times the probability of getting a boy, which is a half, and you want the remaining children to be boys. And you'd have to calculate this one, along with many others than just those two. And then you'd have to add up all these numbers. It's kind of a pain in the neck. It's not a simple thing to do. That is why we want to use the normal distribution to approximate this answer, which is one way of saying don't expect to get the exact answer, but do expect to get a good approximation. Now, there'd be no point in trying to make this approximation if it isn't going to be a good approximation. Okay, so what we're going to do is first let's get rid of this here and let's draw our normal distribution chart or graph. So we're right here. And now, before we can do this, we have to make sure that we are allowed to use this approximation. Remember, NP. Well, N is 75. There are 75 births. And the probability, so that's N, and P will be the probability of getting a girl, which is half. Well, this is half, and you can think of times as of. Half for 75. Maybe you don't know what it is, but come on. Half for $75 is more than $5. It's more than $5. That is, it's greater than or equal to 5. Okay. Probability NQ now. N is still 75, and Q is the probability of not having a girl. But that's also a half. Half for 75. 37 and a half. Yes, it's bigger than 5. These two conditions have been met. Now and only now can you try to approximate this problem by using a normal distribution. And maybe now is when I should have said, let's draw our graph. And actually the reason, and we have two other definitions. The mean for these problems is NP. N is 75, P is a half. I just had that on the board. 75 over 2, or 37.5. So that's the mean. The standard deviation is NP times Q, but the square root of that. It's NP, so it's 75 times P times Q square root. Well, 75 times 1 times another 1 is 75, and 2 times 2 is 4. You like a 1 under here? Fine. Times 1 is still 4. We want the square root of this. Well, I know the square root of the bottom is 2, and the square root is 75. Well, that's the square root of 25 times the square root of 3. And I know the square root is 25. That's where I picked it. If 5 square root of 3 over 2. That is sigma. Sigma is 5 square root of 3 over 2. You want to get an approximation, get an approximation. All right. So we have most of the information. So we want to know what's the probability of getting more than 35 or more. Well, here is 35. Now, here's the deal with these type of problems. You can't use 35. You can go a little bit down. You can go a half down to 34 and a half. Or you can go a half above 35 to is 35 and a half. But just remember, whatever you do use, you want 35 and above. Okay, if you go to 35 and a half and above, that gets most of what you want, but it doesn't get this area here. I'll use 34 and a half. You'll get a little bit more, but the bottom line is you have to get at least what you want. So we have to go to 34 and a half. So let us find the z-score. Z is equal to x, which is 34.5, minus mu, 37.5, divided by 5 squared is 3 over 2. The top is what? Negative 3 divided by 5 squared is 3 over 2's. And let's figure out what this is. Sorry. Once we get this z-score, we'll look up to see how good it is. Okay, so we have 6 divided by 5 times 2 raised to the 0.5. Don't worry about how I do math. Okay, we get 0.8485. 8485. This is very close to negative 8485. And we take our trusty z-table and we see what it gives us. Now the z-table I use will give me that area. So that area, excuse me, that's not exactly true. It would give me below 34.5. And when I look up the z-score, negative 0.84, of course, I'll use 9, 0.849. Excuse me, 0.85, what am I saying? I would use 0.85. Because the number after 4 is bigger than 5. So I go to 0.85, and I get 1977. This corresponds to 1997, did I say, or 77? 1977. 1977. And if you take it away from 1, you, of course, will get 0.8023. And that's our answer. Our answer is 0.8023. That's the probability, well, let me say approximately. Approximately 80.2% of the times, you will get more than 35 girls, or 35 girls or more. When you use binomial distribution, you have to go either a little bit up or a little bit down from the score you really are concerned with. We were concerned with 35 and above, so I went to either 35 and a half or 34 and a half. The reason I went to 34 and a half is because I wanted to include 35 and above. Why don't we review that step at this point? Suppose I want the probability that some score is below or equal to 19. I'm not really concerned if 19 is above or below the mean. Let's suppose 19 is right here. Now, I want to capture all of this area. The thing is, I can't use 19 in the z-score. When I say z equals x, I can put 19. Either go a little bit less than 19, a half less, or a half more. And the half more will be 19.5. 19.5. Now, if I go from 18.5, if I use 18.5, then I have a little problem. I'm not including between 18.5 and 19. The rule is you can't use the score that they tell you to use. That is, you can't use 19. You have to either go a little bit, a half below or a half above. And whatever you do use, it better include, in this problem, 19 and below. So what that tells me is to go up to 19.5. Because here, I'm counting more area than I want, but I'm getting everything that I wanted as well. If you wanted the probability that x is greater than or equal to 27, for argument's sake, put 27 there. Well, either we're going to deal with 27.5 or a little bit below, like 26.5. 26.5 is right here. Now, we must include 27 and above. Well, I hope it's clear then, we better start at 26.5. Because if you started at 27.5, you wouldn't have any of this. You wouldn't have anything from 27 to 27.5. Okay, you have to at least include from 27 and above. So if you go to 27.5, it won't work. So what else? What other choice we have? To go from 26.5 and above. So that's what we would do there. When we go to compute the z-score, it wouldn't, z is equal to x minus mu over sigma. For x, I would not put 27. In this case, I'd put 26.5. That's when you want to use the normal to approximate binomial problems. Let's try another problem. Suppose that you survey 1,000 people, 1,000 voters. You survey 1,000 voters. And 700 claim they voted. Now, people might be embarrassed to say, no, I didn't vote. I didn't have time. People might tend to lie. People would have an incentive to lie about whether or not they voted. Now, I shouldn't say you surveyed 1,000 voters. You surveyed 1,000 people of voting age. And 700 claimed that they did in fact vote. Okay. But now, the stats showed that 61% of eligible voters did vote. Stats showed that 61% of people did vote. Now, of course, if you sampled everyone, well then 61%, when I say everyone, I mean people who are eligible to vote, they're old enough to vote, 61% of them will have voted. And if anything different than, if 62% of the people said they voted, well then some of them lied. If 48% said they voted, well then some of them lied. But when you have 1,000 people, which is not everyone, it's reasonable that 700 could have actually voted. In fact, 61% of 1,000 is 610. So it's not unreasonable that you picked a group of 1,000 people where a little bit more did vote. Now, the problem is as follows. So, what if you want to find this? The probability that at least 700 did vote. Okay? So you survey 1,000 people, and you want to know what's the chances that at least 71% of them voted. Again, when it comes to binomial, and this is binomial, either they did vote or they didn't vote. 61% of the people did vote, 39% did not vote. So to do this by binomial, you would have to find a probability that exactly 700 voted, plus the probability that 701 voted, plus the probability that 702 voted, all the way down to the probability that all 1,000 voted. Towards the end, 1,000, 999, 998, that the numbers are going to be ridiculously small. You know, your calculator will probably just say 0. But you know, they have a lot of zeros and then a 1 and a 4 maybe. But it's going to be really, really small. So maybe at some point you wouldn't have to go all the way up to 1,000, but nonetheless, that is in theory how you would do it using a binomial distribution. But that's ridiculous. What we're going to do is we're going to approximate this by normal distribution. But first, we have to erase the board, and then we need to make sure that we meet the conditions that allow us to use the binomial distribution. We need to make sure that NP, whatever it is bigger than 5, and that NQ, no matter what it is bigger than 5. Well, N, our sample size, is 1,000. And P, probability of success, that is finding a voter, is 61, 0.61. And it turns out that 100 times 0.61, 610. Okay, take your calculator, work that out. N, which is still 100, times Q. Well, if 61% of the people did, so Q would mean not success. That means failure. That is, they didn't vote. If 61% of the people did vote, well then 39% did not vote. And 39 is 0.39. You multiply that by 100, you get 390. And both of these numbers are 5 or more. In fact, they're both more than 5. A lot more than 5. Okay, so we are allowed to use our binomial, normal distribution to approximate the answer to this problem. So normal distribution, let us get our table. It would be good if I stopped erasing what mu is. Remember, mu is n times p. If you think about it, it'll make sense. Mu is n times p. N is 100, p is 0.61. So it's 610. 610. Now, the standard deviation is NPQ. Now, there's no point in using your calculator to type in n times p, because we just did. We got 610. So take the 610, multiply it by q, and then take the square root of that, which is what I'm going to do right now. clear this out. 610 times 0.39 should be around 240. Good. And then I raise this to the half power, which is square root. And I get 15.4. We'll use that. 15.4. This is 15.4. So the standard deviation is 15.4. All right. So let's get rid of most of this. And now let's play normal distribution problem. Now, the problem says at least 700. Here is 700. I want at least 700. I want 700 or more. But I can't use 700. I can either use a half less, which is 699.5, or 700.5. But 700.5 is to the right of 700. That is, I won't have what's in between 700 and 700.5. As a result of that, I am going to use the 699.5. That is what I'm going to use for my x in finding the z-score. Okay. So the z-score is x, 699.5, minus mu, which is 610, divided by 15.4. The top I just know is 89.5. When you divide this by 15.4, you get some answer. Let's see what that number is. $89.5 divided by 15.4. 5.81. 5.81. This here is 5.81. Okay, so very, very, very large number. And the chances of being to the right of 5.81 is 0. The answer is just a little bit more than 0. Okay. In fact, it's very, very unlikely that if 61% of the people voted and you surveyed 1,000 people, that 700 did, at least 700 voted. It's not going to be very likely. Okay. It's going to be a very, very small number. So if you were asked, is this likely? You should say no, it's not. It's very unlikely that this number of people were in fact surveyed. I didn't, going into the problem, to be honest, I thought that it wasn't so unlikely. But I was wrong. All right, let us consider another problem. Do one more of these. Remember, if you have to do a binomial problem, but there's just so, or you're giving a binomial problem, that is, there's two outcomes. They either voted or they didn't vote. Heads or tails, boy or girl. And you have, that's binomial. And you have to calculate a lot of these binomial problems. Well, then think about approximating this binomial problem as if it was normal instead. Or a standard technique for airlines is to overbook. Okay, so you have a plane and it seats 350 passengers, 350 people. Okay? And you're going to book, you can take reservations for 400 people. You're going to take reservations for more people, 400 people, an extra 50 people. If they all come, 50 people do not have receipt. But the probability that they arrive or that they come, the probability that somebody comes to the airport on the day that they claim they're going to come is, say, 0.8. Actually, it's 0.85. The probability that a passenger, in fact, comes is only 85%, which is not as high as the airlines would hope. So the question is, so this particular airlines, they have planes that seat 350 people, and their policy is to book 400. So what is the chances that they overbooked? What's the probability that, what's the probability that people do not get a seat? People do not have a plane seat. That is over 300 people come. 350 people do come. More than 350 people come. If exactly 350 people came, the airline would be thrilled because they don't have to deal with people who don't have seats, and every seat on that plane has a paying passenger. Okay. So what's the probability that they have over 350 seats? Excuse me, over 350 people come. Well, you book 400 people, well, then you have to find the probability that 350 people come, plus the probability 351 comes, all the way down to 400 coming. And this is binomial because either they come or they don't come. But you don't want to calculate these, what is it, 51 probabilities. You're climbing the walls trying to calculate 51 of these probabilities. Then add them all up. So what we're going to do is we're going to approximate this by normal distribution. So we need to find out what NP is. And this time I'll remember that it's mu, and hopefully I won't erase it. The sample size is 400. You're booking 400 people. The probability that they come, well, if you have to start thinking a bit, not running for your calculator. This is more than 10%. 10% of 400 is 40. 1% of 400 is 4. We have way, way over 1%. 85%. So yes, it's going to be way, way over 4. It's going to be 340, actually. Now, what about NPQ? I didn't mean to say that yet. What about NQ? Well, N is still 400, and if 85% of the people do come, that's success, then the failure, Q, is the remaining 15% of the people. And that's also greater than or equal to 5. It's 60. 600, no, what am I saying? It's 60, which is more than 5. All right. So I have my mean. So only because I need the mean, let me put down these answers. The mean is 340, and this is 60. A check would be that it adds up to the total 400. Why is that true? So you have NP plus NQ, you can factor out N. N times P is this, plus N times, Q, N times Q is this. Exactly what I wanted to get. But you know what? N plus Q is 1. Adds up to 100%. And N times 1 is N. And in our case, N was 400. Exactly what we were supposed to get. Okay. That's a little bit of a check. Make sure that you didn't make some silly calculation error. Okay, so now we're almost ready to talk about normal distribution with the graph and all, but we need to know sigma. Sigma is NPQ square root of it. NPQ, the square root of it. NP we happen to know. Multiply that in your calculator by 0.15. And you will get, I can do that, you would get 51. You would get 51. The square root of 51. The square root of 61, just a little bit more than 7. Say 7.1. See how off that is. Okay, so it's a little bit more than 7.1. Actually, why don't we use a calculator to get a better approximation? But at least know it's a little bit more than 7, because 51 is a little bit more than 49, and the square root of 49 is 7. So we want 51 raised to the 0.5 power, 7.14. This is 7.14. So with respect to our graph, we have the mean is 340, and the standard deviation is 7.14. And we're ready to insert our x. Now, we want 301 over 350 people. So here is 350. We want over 350. Okay. That means we don't want 350. So in this case, we can actually use 350.5. We can use this 350.5. So z is equal to x, 350.5, minus the mean, which is 340, divided by sigma, which is 7.14. The top is 10.5. You want to use a calculator to get that? The calculator to get that. That's between you and your calculator. 10.5 divided by 7.14. I'm seeing, what, a little less than 1.5 here. 1.468. 1468. Okay, this is 1468. 1.46. Since only go 2 decimal places, since the third decimal is 5 or over, we're going to use 1.47. And let's see what area that gives us. 1.47 is 9292. 0.9292. That means this area is 0.9292. I want the balance. I want 1 minus that. I want everything which is 1 minus 0.9292. And this is 0.0708. And that is our very, very good approximate answer, which is mind-boggling because this is 7.08%. Only 7% of the times will they overbuck. And what they do at that point is they just let these people sit on another flight for free. They don't care. There's an empty seat on that flight. Trust me, they're not going to take a paying customer off of the next flight to give them your seat. Nor will they give you that free seat if they're the paying customer. I guess that's the same statement. Okay, so this finishes this section on using normal distributions to approximate binomial problems.